My name is Pat Somaru, and I am a production engineer at Meta on the efficiency and capacity engineering team. The goal of this talk is to share some observations, techniques, and code we developed while working with profiler data. Let's dive into it. What is profiler data? Profiler data, often generated by tools like perf, libbpf, or yourkit, is observational data on software and systems. This data consists of snapshots of what is being ran on a system. Engineers use this information to understand how systems are performing. The upper image on this slide contains a single snapshot of a stack of a tiny C program made for this presentation. The lower image contains a flame graph made from 400,000 snapshots like the one above. Flame graphs are a way to view performance data like this. Flame graphs show the relative presence of frames, which are the lines in the upper plot and the boxes in the lower one, in a collection of stack snapshots. The x-axis in a flame graph is the relative percentage of samples a frame is in. The entire x-axis is 100% of samples. The blue arrows on these images show the same data, starting from libc start and going to simulate work. These samples are all weighted, but these weights and their presence or absence vary with the profiler implementation used to obtain this data. This is the program profiled in the prior slide. This program, demo.c, will either call doBusinessLogic or doBusinessLogic and do logging. Both these functions simulate equal amounts of work. Do logging is called half the time. The annotations on the code here correspond to those on the flame graph, showing how much of our runtime footprint each function call is consuming. Now, you may be wondering why this matters so much. Story time. I once used data like this to debug the performance of a slow cache. We'd optimized everything, and the cache was still unacceptably slow. I profiled the app in question and discovered, as these images show, that most of the cache's processing time was being spent converting integer timestamps into strings. Removing this made the cache 10 times faster and, generally speaking, saved the day. Looking back on this, we were lucky in that our performance issue was easily and consistently reproducible. Many performance issues, maybe even most, aren't really reproducible like this one was. Dealing with ones such as these comes with challenges. By challenges, I mean data, lots of data. The stack snapshot and corresponding flame graph here are still contrived, but less contrived. These are more representative of what real-world flame graphs look like. The flame graph on this slide was generated from 10 seconds of profiling, which generated 2 gigabytes of data. At first glance, 2 gigabytes of data to identify a performance issue doesn't seem that bad, because having the flame graph, we can just identify the performance issue and fix it like we did with the cache issue, right? No. We have to collect data to identify performance issues. The 10 seconds we chose to profile our application may not have hit the problematic code paths, which we may not even know are problematic at all. So we have to collect data somewhat continuously. And these 2 gigabytes add up fast, to the point that storing and querying this data becomes difficult. When I say difficult, think about 1/3 of a petabyte a day. This brings me to the real subject of this talk, which is how to deal with this data. This is the takeaway of this presentation. We found that by storing profiler data in a DAG, a directed acyclic graph, we could reduce its footprint by roughly 5 orders of magnitude. We implemented our techniques in a tool we open source named Stow, short for Store Things Optimize. The data footprint benefit of our approach increases with scale. For toy applications, such as the demos in this presentation, we've seen its efficacy drop to 2 orders of magnitude. The queryability benefits of our model, which we will show later, apply to data at all scales. The DAG shown here and the percentages on it roughly matches those on the flame graphs from the prior slides. Structurally, this DAG is a representation of a flame graph. The graphic here roughly shows how one creates this DAG, but we will go into this in depth in further slides. These are Stow's primitives. the units we found with specificity that was just right for keeping data useful to engineers and queryable in our databases. I'm going to explain these by walking through how we found them. We first settled on stack node data being a primitive we wanted to use. When we looked at profiler data, we noticed a lot of it consisted of lots of string data, particularly file paths and function names. We thought about this a bit and analyzed stack traces and found that the combination of symbol, file path, and line number were specific enough to be globally unique. We then hashed this data into a 64-bit integer and replaced all instances of this triple with this integer to reduce the size of the data stored substantially. We found out later on that storing this data as such enabled us to find regressions in reused code across binaries programmatically, as you will see later. While having stack node data reduced the size of our data by a lot, we still had more data than we could comfortably work with. At this point, we had stared at enough flame graphs that we knew call graph data would fit a DAG model well, but we weren't sure how to partition it to meet query pattern and data footprint needs best. We thought about the obvious solution, which was partitioning graphs of binaries call graphs by some unique binary identifier, such as build ID. And we found that, due to the ability to join across these subgraphs that stack node data provided, this actually fit our needs well, so we went with it. This takes us to stack node, the most interesting of these three primitives. The DAG we've been discussing consists of stack nodes. Stack nodes are the vertices of our graph. At a high level, stack nodes are counts of times that a stack node data has been seen at a location in a stack for a particular binary. A stack node's location in a stack is determined by its parent ID, which is also a stack node. Executable ID is associated with stack node to keep queryability high, to enable the scoping of queries to binaries. As the image here shows, a stack node's ID is generated by hashing the stack node's parent ID with its executable ID and its stack node data ID. The right way to think about stack nodes is that their information content is the combination of positional information, location within the call graph, and definitional information, the binary and stack node data associated with it. Deterministically keying stack nodes like this enabled us to perform distributed aggregations of sample counts for the samples field without knocking over our databases with endless deadlocks. This slide shows how we convert the stack snapshot we've been looking at into stack nodes. We first create stack node data IDs and executable IDs per the prior slides. We then invert the stack to enable traversal from the root at libc start to the leaf at simulate work. We then traverse this list, creating stack node IDs and using them to increment or create stack node records as is necessary. We further refined our data model to leverage the cardinality and query need differences across the primitives we discussed previously. When we were developing our data model, we found that stack node data had relatively low cardinality when compared to stack node. This is to say, there were far fewer stack node datas than there were stack nodes. This made sense due to code reuse. Reused code would create a new stack node, but not a new stack node data. We'll get into the benefits of this in a couple of slides. Our data model enabled many cheap indices on stack node data, which is what everyone wants to query all the time and in many different ways because it maps so clearly to their code. Our data model also made indexing stack nodes practical. These indices are primarily used in queries related to the traversal of call graphs, such as queries asking about patterns of call graph. Our indices enabled us to create a performance subtree function, which is used here. This function enables in-database reconstruction of call graph data such that only minimal application-side processing, such as removal of nulls from empty lists, is necessary to convert our storage format into an easily renderable format. This diagram is the result of feeding the output of that query into a JSON visualizer. This format is very similar to that used by the UI library we're using to render this data. Structurally, This format resembles the flame graph, and thereby the DAG itself, enabling straightforward, if not simple, processing of this data. Now that I've showed you what we developed, let's get to what we shared. One of the strengths of this data model is that it enables finding regressions across binaries via static SQL queries in a way that leverages code reuse. One function in one file will only produce one stack node data, enabling the programmatic finding of regressions across multiple binaries. To demonstrate this, I updated demo.c to have do logging make simulate work do 10 times as much work as it would previously do. I then used the CLI of Stow, our open source implementation of all we've discussed so far, to run a profiler to ingest the data output into a database. The profiler used is one a friend of mine wrote while learning how to use libbpf. It is a standard stack sampling CPU profiler. The symbolizer used is BlazeSim. Adding additional libbpf-based profilers should be fairly trivial due to this project using libbpf-rs. Having this data in our database, I ran a generic query shipped with Stow, find regressions, to find regressions across stack node data present across versions of executables. As the results show, it found our regression. To get a better understanding of what this regression looked like, I opened the UI of our server in a browser. I see that for version 2, do logging is taking up way more runtime, as is expected. I also see the data processed while collecting samples and the size of the data sent to the server to be stored in the database. I invite you to clone this repo and give these tools a try. Pull requests are welcome. This brings me to the conclusion of my talk. In summary, the call graph is a graph, and treating it as such has many benefits. Stow leverages this to make call graphs easily storable and queryable. Please take a look at Stow if you would like to get a feel for how these techniques would work for your workloads. Please reach out if you'd like to discuss how these techniques could work for you. Thank you. Any questions?